Hello and happy Friday. So the next topic that we're diving into after we've discussed simple harmonic motion is something pretty similar to simple harmonic motion, and that is what we would call a mechanical wave. So a mechanical wave, as it says here, is a propagation, which is a fancy word for moving through, of energy through oscillations of matter. And so of course something that we say has matter is just anything that we define to have mass. So a really simple example of this is, and you've probably done this at some point, taking a rope and just flicking it up and down. So if you take a look closely at this rope, you are passing energy along this rope. And we would call that energy passage, this wave that we've discussed, and you could do it if you just flick your rope once, right? Or you take the nearest laptop power cord and flick it once, that is a wave pulse. And you are transmitting energy along your power cord or string or rope by literally just putting energy into your rope with that flick. And if you take another close look, while the wave seems to travel along the rope itself does not actually go anywhere. And so the piece of the rope or power cord, whatever you have nearby, is actually just going either up or down. It is simply just going up or down from where it was to begin with. So let's take a look at an animation and see what that looks like. So I've gone ahead and added these animations to the slides that are available online. So if you printed your slides out early, you won't have this in what you've printed out. However, if you go back and look, you will see this animation on slides online. And so what you have here is you have a red block that is simply representing your hand or whatever object is initiating this wave along a string. And if you look closely, you can see this wavelength, that we'll get to in a moment, traveling along the wave from left to right. Further, if you take a close look and watch one of the red dots, those represent individual particles on the wave, or on the string rather. And so those particles, if you notice, simply go up and down despite the fact that this wave is traveling to the right. Now, we call this particular type of wave a transverse wave. And let's get into kind of defining the properties and characteristics of these waves. So as we just saw in the previous animation, the first most easy to discuss characteristic of a wave is that called wavelength. So wavelength is a length by its definition, and you can think of this length as what we call the peak-to-peak or trough-to-trough distance in a particular wave. So this crest, the highest possible point, is also known as a peak, and the distance from one crest to the next crest is what we call a wavelength. And this wavelength has, of course, a Greek symbol. This is a Greek lambda. And it is this symbol that looks kind of like a weird H, and if you would like to take a moment and practice making this symbol, it's not a bad idea. I typically make it like this. It's terrible. Let's try that again. So if you practice something similar to an H like this with a curved top, can get away with looking like a lambda. Now this is a Greek L, it is a lowercase l, which is why we use it for a length. So as we were trying to say, typically we can define the wavelength as a peak to peak, so one crest to the next length, or we could even say trough to trough, so a minimum value to the next minimum value. And of course, these maximum and minimums we have already defined as being one amplitude away from this middle value. Now, one thing that's worth talking about is that we also can just define a wavelength to be the length of a full cycle, meaning when does our wave start to repeat? So, for instance, if I choose this point where I'm going up and I'm about halfway between my trough and my midline, then when does this wave start repeating? Well, I'm going up and then I'm going down. So even though I'm at the same point right here, I haven't started repeating the wave yet. And I don't start repeating until about right here. So once I notice that my wave begins to repeat, then I have traveled one wave length. So one of the things that you will have to do is to be able to look at a graph or a diagram of a wave and determine its wavelength by looking at that visual. Now, before we go any further, we need to discuss the two types of waves that we will see. So the two types of mechanical waves that we see are a transverse wave that we saw in our previous animation, where the particles move perpendicular to the actual energy transport along the wave. So when we add energy over here, our energy travels to the right, but our particles actually travel up and down. So this is at odds with our other type of wave, which is called a longitudinal wave, where the particle motion is actually parallel to the energy that is traveling. So here is a little bit less easy for you to visualize, but if I were to take a spring and just push in and pull out repeatedly, which we will do in class physically when I'm back in the room, you see that you have this kind of cycle where it is a compression, meaning all of these pieces of spring are close together, alternating with an expansion, where those pieces are separated. So this alternating compression and expansion actually forms a wavelength, just like we see in our transverse wave. It's just a little bit harder to kind of visualize. Regardless, here my energy is still traveling to the right because I'm putting energy in from the left end, but now my particles are going in and out, or in this case, left and right. So these are the two different types of waves, and we will talk about their different applications and when you see these two different types of waves. They're both pretty much equally common. A transverse wave, for example, might be literally like an ocean wave or something you'd see in water, while a longitudinal wave is very, very common because sound is a longitudinal wave. So let's talk about that. Whenever you hear a sound, you actually have this alternating cycle of compression and expansion. Now, I will say that there are several different words that have been used for this compression-expansion pair. So compression is pretty common. However, sometimes you actually hear the term rarefaction instead of expansion, because rarefaction is actually more descriptive of the density of the material or the medium that this longitudinal wave is traveling through. So when I bang on a drum, the drum head or the drum membrane that's stretched across the top actually oscillates in and out. And by doing that, it causes the air that is adjacent to it to either compress or rarefact, as we would say. And so you actually see this cycle of density where it's very dense in the dark areas and not as dense in the light areas, kind of repeating. And if you actually map that onto just a high versus low density graph, you see that this looks a lot like the transverse wave or the sine waves that we're used to. So something important that you should actually commit to memory is that sound is a longitudinal wave. And we need to know how a longitudinal wave expresses itself. So let's take a look at another animation. So just like the previous animation, this was not included originally in the slides, but I have added it to the slides that are available online. So this right here is an animation for a longitudinal wave. And the features that you should look at are these red particles that are just simply, you can imagine, air particles that are just in the air. And when you apply some energy to the left end, you can see that this wave travels to the right. So this is the direction of the energy flowing through the air. Meanwhile, the air itself doesn't really move. If you take a look at one of these red dots and follow it for a moment, you see that it just goes back and forth. It oscillates. And so energy transports through this by this cycle of compressing and, as we said before, rarefaction, where we are having this alternating high density versus low density. And even though it may kind of hurt your brain to look at this for too long, it's important to note that the particles themselves don't actually travel all the way to some other object. So when I make noise, the air particles that are coming out of my mouth are not actually reaching your ears. But what is reaching your ears is this energy that has been transported along those air particles. So one of the natural conversations that follow up discussion of sound is simply how fast these waves travel. Because we know something that's very common to normal discussion of sound is its speed, the speed of sound. And so the speed of any wave depends on what we say are the properties of the medium that it travels through. So a medium is whatever material a wave is traveling through. So this is important to know. So it's a material. So you've probably put your head underwater at some point and made a noise or heard other things underwater, and those are sound waves that are traveling to your ears. They're just traveling through water instead of air, so they sound a little different. So part of that has to do with the fact that when you change the speed of a wave, the wavelength and frequency are dependent on that speed. So any change in any of these three kind of affect the end result of that wave. So there are several different things that we need to take away from our understanding of the speed of waves. Number one is this equation. The speed of any wave could be found by the product of its wavelength, so wavelength, and its frequency. And again, this is the frequency that is in hertz, not the frequency that would be in radians per second. So any wave that we deal with, we can discover or use the speed of that wave to relate wavelength and frequency for that wave. Now, if you're curious, the speed of sound is something like 343 meters per second, and that is the only thing that you will have to submit to me to prove to me that you have actually watched this whole video. So turn that in through Haiku. Now, the last thing that we want to talk about is not necessarily the speed of waves in air, but also the speed of waves in physical mediums that we can really interact with. So one of these that's really common is a string or a cord. If you've ever taken a rubber band and stretched it tight and plucked it, then this is the kind of wave that we're talking about. The speed of those types of waves depends on three things. Well, really two things. One of those, probably the most important, is the tension in that string. So as you can see here, the speed of the wave is proportional to the tension or directly related to the tension. The higher the tension, the higher the speed of the wave in that medium or that string. The second thing is a little less common, and this is what we would call the linear mass density. And here it's represented by a mu. So this is not the same mu that we used for coefficient of friction. This is a different meaning. So this is what we call linear mass density, and it is the mass of the string divided by its length, as you see right here. All that means is, if we take a string and we have a heavier string compared to a lighter string, then that is actually going to have a reverse effect on the speed of the wave. So the speed of the wave is actually going to be faster on a lighter string. And you may know this if you play any string instruments. The higher notes come from the lighter strings and the lower notes come from the heavier or thicker strings. So if you've never wondered why that is, this is a physics reason why. Now the final property that we're going to discuss right now is that of the energy that is transported along these waves. So we've discussed wavelength, we've discussed frequency in a short version, and we have discussed the speed of the wave. Now let's actually talk about this energy that we are transporting through these waves. So the measure of the energy transport is usually called intensity, which is a capital I for us. And it's measured in units of watts per square meter. So if you've ever had a really powerful sound system, that's because it is putting out a lot of energy per square meter. And that energy per square meter is also a function of time. The more energy you put out in a short amount of time, the higher the intensity of that sound. So typically, the intensity of a wave depends on two things. One of those is simply the amplitude of the wave. The other is the distance from the source. And you can see that these two are at odds. Obviously, the higher amplitude of a wave, the more intense it is. There's simply more power put into the oscillation that started that wave. Whereas the further you are from the source, the louder doesn't really translate, right? So the further you are away, the less intense that sound is. And this kind of makes sense, but it's really worth pointing out the relationship between these two variables and the energy that we actually receive from a particular source. Now feel free to take a moment and pause and absorb the things we've already talked about, because we're going to shift gears a little bit and talk about waves and how they interact with the world around them, essentially. So let's go back to the example where you take your power cord that may or may not be nearby and you give it a flick. And so this right here is what we would call a wave pulse. And so that pulse would travel along the string, and usually it'll just run out and stop going anywhere. But if you flick it hard enough, it will go all the way to where your cord is plugged into the wall. Now, what happens when your wave pulse gets to the wall is kind of interesting if you think about it. What happens tends to be that it will hit the wall and then it will reflect off of the wall. Now, if you haven't flicked it hard enough, and I'm not saying you should, because after all, this is a power cord and it's, you know, attached to an electrical socket. Maybe you should do this with a string or any longer piece of thread that you have lying around. But if you flick it hard enough, it will hit that fixed position on the wall and it will reflect backwards. And the way that it reflects depends on how it is attached. So if it is attached in a fixed way, it will reflect with what we say is inverted phase. So if you see this right here, this is how we talk about phase. So my wave is going in where it's simply above this middle line the entire way, and when it hits this fixed position, it reflects in the opposite direction. So now it is all below this midline. And so that may be one reason you don't see this reflection necessarily. However, if you take this off, and let's see a good way to think about it, we probably won't be able to see this very easily. It's not very easy to replicate in the physical world. If this object or the string is hitting something that is not fixed, it will actually reflect back the same way, on the same side. And we say that is in the same phase. So the way that we summarize this, and I'm sorry for the convolution, the way that we summarize this is that when a wave runs into a medium of higher density, so for instance, the wall right here is a little higher density than our string, then it will reflect with what we say is inverted phase. So it will reflect back with an opposite wave shape, we would say. When it strikes a medium that is lower density, so when the string runs out of string and there's nothing but air over here, that's probably lower density than the string. It will reflect back with the same phase. So whatever we had going into the wall will just come right back out. So the reason that we have this discussion of reflection is because when you deal with, for instance, a musical instrument, the reflection of waves back and forth along the string is what actually produces this constant sound that we can hear. So let's take a little bit more of a look at how these waves travel along a string. So to get to how these waves in a string form a musical note, we need to understand something called interference of waves, or superposition of waves. Now, I believe we've discussed superposition before, but the word superposition literally means lay on top of. Super meaning on top of or above, and position, well, you should know what position means at this point of the year in physics. So let's take a look at this diagram on the left. So let's say you and a friend have a rope that is held between you. One of you flicks the rope up from the left end, and the other flicks it down from the right end. When those waves actually overlap, they will do what we call is interfere. And interfering really doesn't mean they mess with each other. What it means is that they are combining at this particular instant in such a way that their amplitudes are additive, meaning you add them up. So because this amplitude coming from the left is positive, and this amplitude coming from the right is negative, when they overlap at this instant in the middle, you see that there is no displacement. That's because these amplitudes have essentially canceled each other out for the instant when these two wave pulses completely overlap. The fun thing about this, though, is that as soon as that overlapping is over, they just go along their merry way. The reason why is that energy is still transporting in the same direction. And they really haven't interfered, as we call it. They've simply interacted and overlapped for that one particular instant. And then the pulses themselves are unchanged. And they continue on. So interference may be a bit of a misnomer, but that is what we've always called it. So let's look at a different example of interference. So now you and your friend both flick the rope up from both ends. When these two pulses overlap, let's say they both had an initial amplitude that's positive A. When they overlap, they again add together, and now you have, looks like a larger pulse. And the reason why is, again, they add together, and now you have an amplitude that is twice as large. And again, once they are done interfering, they just continue on their way, unchanged from the initial wave pulse. So these are the important aspects to take away from our baseline understanding of superposition of waves. So let's go ahead and take a look at a little bit more of a complicated example for superposition. So here we have three different examples for wave superposition, and we have a little bit more specific terminology to go along with it. So let's take a look at this diagram A here. You see that, if you look closely, these peaks are aligned, and these troughs are aligned, and that repeats on and on. So because these waves are overlapping such that the positive is aligned with the positive, or the positive displacements rather, and the negative is aligned with the negative, we have what is called constructive interference. So that means that because these waves, when they overlap, add together, that means you end up with a larger overall displacement, both up and down. So we call that constructive because these two waves essentially add together for an overall bigger wave. So the same thing would be true if, say, you and your friend both stand next to each other and sing the same note. Your waves essentially add together constructively for a larger overall louder sound. So now let's take a look at what happens when they don't line up. So here we see that the positive actually lines up with the negative displacement, or the negative actually lines up with the positive displacement. In this case, we have what is called destructive interference. Because these two amplitudes are they're oppositely aligned, you have the positive amplitude, positive displacement, adding up with that of the negative. And the net result is that these two things cancel out. Now, this is a very important phenomenon. If you've ever been to a theater, or maybe seen a music show where you couldn't hear very well in your seats, that may have been because the sound that was coming from the speakers destructively interfered at the location where you were sitting. And the waves that you were hearing were a lot softer than they should have been because their amplitudes were not aligned properly, so that you got a louder sound. You actually ended up with a much lower sound. You couldn't hear what was going on. And you can have something in between destructive and constructive interference, and that's what we call partial destructive or partial constructive interference more often. So this partial interference, you can see, all right, I have my peak, and it is kind of just aligned up in the middle here, and these things do still add up, but they add up in kind of a weird way. So here I see, all right, this is my amplitude, this here is also my amplitude, but it adds to nothing. And so you end up with something that's kind of in the middle. It's not really bigger too much, it's not really smaller too much. Overall, you just have kind of a different wave that results from this. And the fun thing here is if you actually go and you look at the recording of someone's voice or someone singing or a musical instrument, You see these kind of waves all the time. However, they're a lot more interesting looking because when you actually have someone's voice or a musical instrument, you have a lot of different sine waves that are interfering, and they make something that looks completely different from just one of these regular plain old sine waves. So what you need to take away from this is you need to be able to essentially add up the amplitudes of two different waves or wave pulses when they are aligned in certain ways. So that's what you'll be doing for your homework assignment over the weekend.